of the most profound questions humanity has ever asked. This isn't just about numbers, it's about our place in existence, in time, in space. Over the next 2 hours, we'll travel through time and distance, from atoms to galactic superclusters, and explore what modern science knows and doesn't know about the true size of the cosmos. Buckle up, this is Astrotech Universe, and we're heading to the edge of everything. The observable universe. The observable universe is the part we can see, and that doesn't mean it's the whole universe. Because light takes time to travel, we can only see out as far as light has had time to reach us, about 13.8 billion years. But here's the twist. Due to the expansion of space, the true distance to the edge of what we can observe is about 46.5 billion light-years in every direction. That's a diameter of 93 billion light-years. We're not at the center of the universe, but we are at the center of our observable universe. And every observer everywhere is at the center of theirs, this of cosmic measurement. To measure something this vast, we need special units. 1 astronomical unit, AU. Distance from Earth to the Sun, about 150 million kilometers. 1 light year, distance light travels in a year, roughly 9.46 trillion kilometers. Parsec 1, about 3.26 light years, often used in galactic mapping. These units help us understand sizes ranging from solar systems to intergalactic distances. The Milky Way, our home galaxy, is about 100,000 light-years across, and yet it's just one of over 2 trillion galaxies in the observable universe. Light, time, and distance. Light is the cosmic messenger. It travels at 299,792 kilometers per second, the universal speed limit. But more importantly, light gives us a window into the past. When we see the sun, we're seeing it as it was 8 minutes ago. A star 1,000 light-years away? That's a 1,000-year-old image. The deeper we look into space, the further back in time we see, all the way to the birth of the cosmos. That's why distance in astronomy is always tied to time. The expanding universe. In 1929, Edwin Hubble made a profound discovery. Galaxies are moving away from us, and the farther they are, the faster they recede. This revealed that the universe is expanding. It's not that galaxies are flying through space, it's that space itself is stretching. Think of raisin bread in the oven. As it bakes, every raisin gets farther from every other raisin. Not because the raisins are moving, but because the dough is expanding. That dough is space-time. Redshift and expansion rate. This expansion leads to something called redshift. As light travels through expanding space, its wavelength is stretched. It shifts toward the red part of the spectrum. The more redshifted the light, the farther away the source galaxy is, and the faster it's receding. This relationship is encoded in Hubble's law and allows us to measure vast cosmic distances. The cosmic horizon. The universe may be 13.8 billion years old, but due to the expansion of space, we can see galaxies that are now 46.5 billion light-years away. This boundary is called the cosmic horizon, the edge of what we can possibly observe. Beyond this horizon, light hasn't had time to reach us since the beginning of the universe. It doesn't mean those regions don't exist. It just means they're causally disconnected from us. We may never know what lies beyond. The cosmic horizon is a natural limit, imposed not by technology or telescopes, but by the fundamental structure of space and time itself. Inflation and the first moments. Right after the Big Bang, the universe underwent a mind-boggling phase called cosmic inflation. In a fraction of a second, the universe expanded faster than the speed of light, not violating physics because space itself was expanding. This expansion explains the uniformity of the cosmic microwave background and how structures like galaxies formed from tiny quantum fluctuations. It also means that the universe could be much, much larger than what we see, possibly infinite. The observable universe might be a microscopic patch in a grand cosmic tapestry. The shape of the universe. The universe might be flat, closed, or open, and its shape affects whether it's finite or infinite. A flat universe means parallel lines never meet. It extends forever. A closed universe curves back on itself like a sphere, finite but without a center or edge. An open universe is saddle-shaped, infinite and ever-expanding. Measurements of the cosmic microwave background show the universe is flat to within 0.4%, strongly suggesting it may be infinite in spatial extent. But even a very large, closed universe can appear flat to us locally. Only about 5% of the universe is made up of normal matter: atoms, stars, gas, and planets. Dark matter, which makes up 27%, doesn't emit light. We detect it by its gravitational effects on galaxies and galaxy clusters. It binds galaxies together and shapes the cosmic web. Dark energy, comprising 68%, is even more mysterious. It causes the expansion of the universe to accelerate, pushing galaxies apart faster and faster. It's the dominant force in the cosmos and determines the ultimate fate, and possibly the final size, of the universe.
Is the universe infinite?
Could the universe be truly infinite? If space is flat and expansion continues forever, then yes, it might go on without end. An infinite universe has profound implications. It could mean that somewhere, far beyond our cosmic horizon, every possible configuration of matter has occurred, even duplicates of Earth, or versions of you. We'll never observe infinity directly, but theory and observation suggest that our universe could stretch endlessly in all directions. The multiverse.
What if our universe is just one of many?
This is the idea of the multiverse, a vast collection of universes, each with different laws of physics. Some models of inflation suggest eternal inflation, where new universes are constantly being born in a vast, inflating space. Others come from quantum mechanics or string theory. If the multiverse is real, then the size of our universe is just a footnote, one bubble in an infinite sea.
Simulation hypothesis.
Here's a radical idea. What if the universe isn't real, but a simulation? According to the simulation hypothesis, we might be inside a computer-generated reality, created by a highly advanced civilization. It's not science fiction anymore. Some physicists and philosophers take it seriously. In this case, the size of the universe is merely a rendering, projected as needed. Vastness becomes an illusion, a clever trick of cosmic programming.
How we measure the universe.
Measuring the universe takes ingenuity. Astronomers use parallax to find distances to nearby stars, triangulating from Earth's orbit. Cepheid variable stars, which pulse in a predictable way. Type Ia supernovae, standard candles used to gauge the size of the cosmos. Cosmic microwave background giving a snapshot of the early universe. Through these tools, we've mapped billions of light years, but we've only just begun. What does size even mean? In the quantum world, particles exist in fuzzy states, without a definite location or size. In relativity, time and space bend with mass and energy. To a photon, which travels at light speed, time doesn't pass. The journey across the cosmos is instantaneous. So what does size really mean in a universe where the rules change with scale? Maybe the question isn't just, how big is the universe? But what does it mean to measure anything at all? The universe might be 93 billion light-years wide, or infinite. But either way, it's everything we've ever known, every star, planet, and possibility. Thanks for watching Astrotech Universe. If this blew your mind, subscribe, like, and share. And drop a comment below. How big do you think the universe really is?